Welcome to Investigating the Universe, where we unravel the mysteries of technology and beyond. Today, we delve into the fascinating world of quantum computing, a realm where the laws of physics as we know them take a back seat, and a new set of rules come into play. So what exactly is quantum computing? Simply put, it's a type of computing that leverages the principles of quantum mechanics to process information. Unlike traditional computers that use bits to process information in a linear manner, quantum computers use quantum bits or qubits. Here's the kicker. A qubit can exist in multiple states at once thanks to a property known as superposition. This means it can be both a 0 and 1 at the same time. This is a radical departure from traditional computing where bits can only be 1 or 0 but not both. But that's not all. There's also a concept called entanglement. In the quantum world, two qubits can be entangled, meaning the state of one qubit can instantly influence the state of the other, no matter the distance between them. It's a phenomenon so strange that even Einstein referred to it as spooky action at a distance. These quantum properties give quantum computers the potential to solve complex problems that are currently beyond the reach of traditional computers. From cryptography and optimization to drug discovery and climate modeling, the possibilities are vast and exciting, but it's not all smooth sailing. Quantum computing is still in its infancy, and there are numerous technological hurdles to cross. For instance, maintaining the delicate states of qubits is a significant challenge. Plus, there's the issue of quantum error correction, which is far from being a solved problem. While quantum computing holds immense potential, it is not without its challenges. But then again, isn't that what makes any journey worth taking? Stay tuned as we explore these challenges and more in our journey through the quantum universe. One of the main issues with quantum computing is achieving what we call quantum supremacy. This term, seemingly plucked from a science fiction novel, refers to the point at which a quantum computer can perform a calculation that is practically impossible for a classical computer to do within a reasonable time frame. Quantum supremacy is a challenge because it demands not just the creation of a quantum computer, but one that's powerful enough to outperform the best of our classical computers. This is no easy task. We're talking about a machine that can manipulate quantum bits, or qubits, with such precision and control that it surpasses the computational power of supercomputers that have been refined over decades. The current status of quantum supremacy is a hot topic of debate in the scientific community. In 2019, Google claimed to have reached quantum supremacy with their 53-qubit processor, Sycamore. They announced that Sycamore had performed a specific calculation in just over 3 minutes that would take the world's most powerful supercomputer around 10,000 years. However, IBM, a prominent player in the quantum computing field, disputed this claim, arguing that the task could be accomplished by a classical computer in 2.5 days using a different approach. This back and forth underscores the primary hurdle in achieving quantum supremacy, the difficulty in defining and measuring it. Quantum computers, by their very nature, are designed to solve problems that classical computers struggle with. So, how do we compare apples to oranges? And even if we do reach quantum supremacy, how do we verify it? Moreover, having a quantum machine that can outperform classical computers in one very specific task doesn't necessarily mean it's generally superior. It's like having a sports car that can outspeed a regular car in a straight race, but may not fare as well in a crowded city with traffic rules and speed bumps. So, quantum supremacy, while fascinating, remains a formidable barrier in the progress of quantum computing. The journey to it is filled with scientific intrigue, debates, and discovery. And while we may not be there yet, the pursuit of it continues to push the boundaries of what's possible in computing. Another significant challenge in quantum computing is quantum decoherence. Let's delve into this fascinating yet complex concept. In the realm of quantum computing, decoherence is the unruly child that refuses to play by the rules. It's a process where quantum systems lose their quantum properties, like superposition and entanglement, and start behaving more like classical systems. Imagine you're at a party and you're trying to have a conversation with a friend, but the music is too loud, people are talking over each other, and someone just dropped a glass in the background. All these disturbances make it hard for your friend to hear what you're saying. This is akin to quantum decoherence, where external disturbances cause quantum bits or qubits to lose their delicate quantum state. Decoherence is a major hurdle because it can lead to errors in quantum computations. It's like trying to solve a complex mathematical equation, but the numbers keep changing before you can find the answer. This is why quantum systems are typically isolated and kept at super low temperatures to minimize interactions with the environment. But, as you can imagine, maintaining such conditions is not easy, nor is it practical on a large scale. So how do we overcome this issue? Scientists and researchers are exploring several solutions. One approach involves using error correction codes, which can detect and correct errors caused by decoherence. Another strategy is to design quantum systems that are inherently resistant to decoherence. There's also a lot of interest in topological quantum computing. This is a type of quantum computing that uses anyone's particles that exist only in 2 dimensions to store and manipulate information. The advantage of this approach is that anyone's are less susceptible to decoherence, making them promising candidates for quantum computing. So, while quantum decoherence presents a significant challenge, it should not be seen as an insurmountable obstacle. With continued research and technological advancements, we are inching ever closer to achieving practical and reliable quantum computing. Quantum decoherence, though a major hurdle, is not an insurmountable one. The third challenge we face in quantum computing is quantum error correction. In the world of classical computing, error correction is a well-understood concept. Computers are adept at detecting and correcting errors, and they do so by using redundancy. They store data in multiple places and then compare it. If there's a discrepancy, it's an error and they correct it. It's a straightforward process. However, in quantum computing, error correction isn't as straightforward. The quirky nature of quantum bits, or qubits, makes this task a lot more complex. Unlike classical bits, which are always in a state of either 0 or 1, qubits can exist in multiple states simultaneously, thanks to the quantum phenomenon known as superposition. This means that a qubit can be in a state of 0, 1, or any combination of both at the same time. This superposition of states complicates the error detection process. You see, in quantum mechanics, the mere act of observing a system changes its state. This is known as the observer effect. So if we try to observe a qubit to check for errors, we risk collapsing its superposition state and altering the information it holds. This makes traditional error detection methods unsuitable for quantum computing. So how do we tackle this? Enter quantum error correction. It's a set of techniques that aim to protect quantum information from errors due to decoherence and other quantum noise. Quantum error correction codes are designed to detect and correct errors without directly measuring the state of the qubits, thus preserving their delicate superposition states. However, implementing quantum error correction is no easy feat. It requires a large number of qubits and a lot of computational resources. Developing practical and efficient quantum error correction codes is a significant area of active research in quantum computing today. Quantum error correction, a crucial aspect of quantum computing, remains a complex issue to address. It's a fascinating challenge that continues to spur scientists and researchers worldwide in their quest to build a practical and powerful quantum computer. As we've seen, quantum computing, though promising, is fraught with challenges. This exploration into the universe of quantum computing has taken us through a labyrinth of complexities and potentialities. We've delved into the concept of quantum supremacy, the idea that quantum computers can outperform classical computers in specific tasks. While this is an exciting prospect, we're still in the early days of realizing its full potential. We also touched upon the intricate issue of quantum decoherence. This phenomenon, where quantum systems lose their quantum properties to the environment, is a significant hurdle in the path of quantum computing. It's like a ticking time bomb, threatening to disrupt the quantum state before we can even put it to use. Our journey didn't stop there. We navigated through the maze of quantum error correction, a critical aspect of quantum computing. The process of correcting errors in quantum bits, or qubits, is fundamentally different from how it's done in classical computing. It's a complex task, but it's also a crucial one to ensure the reliability of quantum computations. These are just a few of the many challenges that scientists and researchers are grappling with in the field of quantum computing. But every challenge is an opportunity for discovery, for innovation, for progress. The road to quantum supremacy may be filled with obstacles, but overcoming these obstacles could open up a whole new realm of possibilities that we can't even begin to imagine today. The journey of quantum computing is far from over. In fact, it's just beginning. And as we continue to unravel its mysteries, we are learning more about the universe within us and the universe beyond us. Thank you for joining us on this journey into the universe of quantum computing. If you enjoyed this video, please subscribe to Investigating the Universe and don't forget to like and share this video. Until next time, keep exploring the universe within and beyond.